Hi guys, this is Terry with Futures IO. It is my honor to welcome Greg, aka NJAMC, for today's webinar on machine learning concepts. The bullet points for today's webinar are a brief introduction about Greg, machine learning approaches, data selection and pre-processing, and results in network debugging. Now, during the webinar, if you have any questions, you can type them into the questions box and we'll do our best to answer them at the end of the event. Also, if you're watching this on YouTube, please do us a favor and give us a thumbs up if you enjoyed the webinar. And as always, please feel free to share, comment, and subscribe to our channel. It really helps us a lot. And now, also, don't forget that you can start to follow us on Twitter and Facebook and now YouTube as well at Futures IO. And without further delay, I'll hand it over to Greg. And you should get the pop-up box.
Okay. Are we live? Can you see the agenda?
Looks good.
Okay. All right. Well, thank you, Terry. I'm honored, as usual, to be invited back, especially on such a exciting topic. So, machine learning, as you know, is pretty much in the news just about every day, and it's getting more and more exciting with the release of some of the tools that are out there. So what I'm going to try to do is go over some of the work that I've been focused on for the last probably year and a half or so with all these technologies coming out, and give some hints and tips that may help others that are going down this road. The unfortunate part with machine learning is there isn't a out-of-the-box solution. So right now, you need to have a little bit of, I'd say, a strong background in what machine learning is all about and what you're trying to do to be successful. So, but with that, let's just move on. So just a quick introduction. I've been involved in trading for about 6 years, mainly through Futures IO and a couple other locations as well. My background: I'm an electrical engineer. I'm a commercial software author. I've got numerous patents and patent submissions, 2 of which involve machine learning. I've worked in upper-level management for medical devices for over 25 years in R&D as well as manufacturing. And recently, last year, I started a machine learning trading tools business. So that's my background. What I want to focus on today is more on the order of deep learning. So I've got a definition here from Wikipedia. I'm not going to read it, but the crux of the matter is that deep learning is focusing on high-level abstraction of data. So much like some of the face recognition software and image recognition software that you may have seen out on the net, this is another opportunity for these intelligent systems to learn abstractions about stock market data as well. So this wasn't really easy to do in the past without the concept of deep learning because the abstractions weren't high enough, and you really couldn't sort out whether or not you were trading on noise or whether or not it was just luck that you were following at the time. So, but currently this is a bit of a craft. So again, machine learning is a makeup of tools, not solutions. It requires experimentation, understanding, and debugging. Nothing useful, as I've said, out of the box for end applications at this point. I will give a little caveat on that the rate that I see machine learning going at these days, I would hope within a year or two that we would start getting higher level tools out of the machine learning communities. There's also no hard and fast rules to a solution. So it depends on what you're trying to do and how you want to approach it. There's unfortunately numerous solutions to any problem. So it depends on how you want to start out and what you're most comfortable with as to how to move forward. That makes recommendations from other folks a little more difficult because without knowing the full approach to your problem, it's a little difficult to understand how to give feedback We'll talk a little bit about general feedback and how you might be able to debug your own network and what you might be able to do as we go through here. Again, it's a little bit of detective work that you're going to learn to get through this. The other challenging part of machine learning is it works as a system. It's difficult to isolate sections. The other portion is that the training is actually set up through a random system. So if you look at the constants and learning weights that you've acquired from a particular learning set, the next time you set it up and train again, they're going to be completely different. So you won't get the same result each time that you run a training. And as always, garbage in is garbage out. So today we're going to focus a little bit more on the in because that's critical for you to get anything useful out. So let's talk a little bit about approaches. This is going to be a little bit of a review for folks plus a little introduction to a new concept as well. Supervised learning, most of you are probably familiar with. So essentially this is where your output is a function of your input, and you actually have pairs of training data. So you know X and you know Y. So you know what the output's supposed to be for any input that you give the system. And this is supervised learning because the training system is going to take those pairs and assure that they work in your end solution. Supervised learning can be used for regression and classification. It's also a cost minimization problem. So how your training system works is by reducing the amount of error in your Y that you've told it is correct and the Y that it generates out of the function that it's trying to create. There's also unsupervised learning. This we don't use this as much, but it's out there and it works for certain tasks. In this case, all you know is the input. So what you're trying to do is you're trying to take the input and you're trying to look for hidden structure from this unlabeled data. This can actually be done in some of these image nets that people have developed with deep learning as well. So I was going to say that it's kind of a k-means cluster type of concept, or it can be used for anomaly detection as well for outliers. And I've seen it listed that principal component analysis actually another form of unsupervised learning. I tend to think of that as more of a matrix mathematics. But in unsupervised learning, what you're trying to do is you're trying to find things that are similar. So in the case of image data, you can actually see that features deeper into the network might represent certain things like an eye of a person, or the nose of a dog, or the ear of a cat. So those are some of the things that get developed through a learning system. And these are actually generated without labels, or they can be. So what happens is the system goes through and finds these features. It's only when you start to do a supervised learning that these features get assigned to labels. But it's important that these structures form in your neural network so that they can be labeled if that's your end goal. A more recent type of learning is the semi-supervised learning. So in this case, you know your input, but Y is dependent upon some future action. So it's not as straightforward as supervised learning. A good example that DeepMinds has come out with an application that learns how to play video games. So, and some of the actions that it might perform are going to be to move left, right, fire, or do nothing. So those are some of the actions, and if you fire now, you won't know for some period of time as to whether or not that was beneficial or not. So because that bullet may not have hit its target yet. So you have this delay in essentially the reward that you would get back from the system. There's a big group of research in this area called reinforcement learning. This is generally what is thought of as semi-supervised learning. In this case, you take the environment, which is the world. the system decides an action and then it waits and gets a reward back. It's a form of learning a Markov decision process. So you could learn a policy function. So essentially the policy function is, if you see this, then fire. So the other type of learning that can be done here is also a value function that says that if I do X, then my future value is Y. So those are, it's kind of an indirect way of generating what action you should take. This is generally used for classification of action. So essentially these reinforcement learning systems are trying to figure out whether or not it should go left, right, fire, or do nothing in the case of a video game. The other portion of this is it's also a minimization of cost, but it's indirect, because in actuality what you're trying to do with a system like this is you're trying to maximize future reward. Now, deep learning, the nice thing about some of the tools that are coming out today are they're what I call building blocks. So what is happening is these small structures or cells are coming out that have certain advantages over other cells. So in the case of deep learning, you've got there's probably these three major structures that exist. The deep neural network is the same thing as kind of the neural network of the past. So it's the same type of structure. It's a matrix multiplication with a potential bias attached to it. What you'd usually do is add a nonlinear activation to it. And this type of network can be used for any purpose whatsoever. So the image processing and some of the other interesting toys you may have seen on the network are based around convolutional neural networks. So what happens here is there's an enormous amount of math that's going on in the background, but what you're doing is you're forming filters that activate upon the presence of certain stimuli to those filters. So there's this works on 2D, 3D, I've seen even a 1D type of convolutional neural network. Again, you have nonlinear activations in this type of structure. It's generally used for image processing, image recognition, and image classification. There's a few other things that are being played with in this area as well, but those are the biggies right now. So the next major building block is the recurrent neural networks. So these are an attempt to form memory in a neural network. So there's a couple of major, I guess they're specializations of the RNN, which is the recurrent neural network. All of these have their own problems. The problem with the RNN is you'll have a problem with vanishing gradient and vanishing, or sometimes an escalation of your gradient as well over time. So what they've done is they've developed these other cells, like a long short-term memory cell, the LSTM, as well as the gated recurrent unit. The LSTM is probably the most popular and most functional of these building blocks. This gets around some of those limitations that are well documented out on the net for the RNN. You can stack multiple LSTMs together and get some very interesting functions out of those. This particular building block is used for natural language processing, so essentially translation between languages, understanding structure of sentences. It's used for time-based data, and it's also used in speech recognition. So the other portion here too is that although I didn't put it in here, there's a non-linear linear relationship with these types of structures as well. It's just inherent in how they work. But I'd say in all cases, for a deep learning system to learn something interesting, you need to add the nonlinear activations into it. Without the nonlinear activations, all you have is a linear system, which isn't going to buy you a whole lot of complexity. All you're going to get is a lot of computation with a very simple output. The nice thing about the newer tools that are coming out as well is that you can mix and match these types of cells as you see fit to try to solve unique problems. So the complexity of how these cells work is hidden by TensorFlow as well as Microsoft's product out there. So you can mix and match, and you don't need to worry about the gradient descent or that type of complexity of how to piece these things together. So we'll talk a little bit now about data selection and preprocessing. So the most critical part, and sometimes people forget this, is you need to define the problem. So some people try to jump right in and start throwing data together and without a clear understanding of what it is they're trying to do. So make sure you have a good idea of what it is you're trying to accomplish. You need to understand that problem. You need to understand if there's what data might be needed and what corner cases might exist. So like, is there a divide by zero, or are there outliers that are generated in certain instances with your problem and with your input data? You need to understand the input data that you're actually giving it as well. So to blindly take data and feed it into a system like this can be very frustrating for you, because what you might get is good results on your training data, but on your test data it starts to fall apart. And that's where you really need to start looking at your input data to make sure that it meets certain restrictions we'll talk about in a little bit. The other important part is, what is your end goal? What output are you expecting? So are you expecting a classification? Are you expecting a regression? So are you expecting a number to come out of this? It's important to know that, because that actually drives some of the topology of your neural network. So the topology is just simply what's between the input and the output of your neural network. And all the stuff that we just talked about help drive what cells you're going to put in between there. So is it going to be a DNN, a CNN, or an RNN type of structure, or a mixture of all of the above? Then you want to set out and design the solution. So what is the input data? What pre-processing will occur? Again, the topology that will be used. And then you also need to validate that design. I don't have a specific slide on that, but at the end, if someone wants to ask about some tips on how to validate a design, this is very difficult and to be able to validate your system, because without known data, it's very difficult to do that, especially with the type of data we get from the stock market. So again, you also want to do some consideration as part of your design on what is it you're trying to do. So is there timing and latency issues? And that's going to depend upon if you have a high-frequency trading system, a scalping system, a day trading system, a swing trading system, or you're simply just trying to generate an indicator that has those types of speeds. The other important concept is slippage, and that's based upon order type. So market orders, you'd better add slippage based upon the span of your bid to ask. The other ways to get around some of these is use limit orders. That generates some additional complexity because you might not get filled all the time. Stop orders might have slippage as well, and certainly stop limit orders have their own considerations as well. The other issue to consider is noise. Noise is really going to be your enemy, because noise is what slows down convergence of your system. This is what probably the training system, the training process tries to overcome and has the most difficult part doing. So the less noise that you can feed into your neural network, the faster it's going to converge to a solution, so you can either move on with your final solution, or at least determine that there's some modifications that you need to make. So what you'll find is that if you're trying to do things on the order of seconds, you might end up with a lot of noise into your system. Again, it depends upon what problem you're trying to solve. So, I'm talking in general that you're looking at a time-based chart. and there's going to be a lot of price action in a few seconds that don't necessarily mean anything to the output of your system. You might actually see that on the minute charts as well. So depending on what you're trying to do, you might want to start at a higher time frame like days or hours or even 30 minutes and see if you can nail that down. That's another trick to be able to validate your system, is go to a higher time frame and see if your system works there. If it starts to work at the higher time frame, then it's probably noise that's bothering you. So you might need to look at your data input, and maybe there's some additional ways that you might be able to filter it or deal with that data. The other consideration is exotic chart types. There's plenty of statements on the Big Mike's, or I'm sorry, Futures IO on like the Renko style charts. So just be careful of that. Make sure you understand what your open, close, high, and low are. Some of the machine learning considerations, this is going to touch on what we've already talked about, but topology is a deep neural network, a convolutional neural network, or a recurrent neural network topology. So the data that you're feeding this thing, do you have enough? Is it correlated? So has it been properly pre-processed? Is it stationary, or is the topology designed to handle this? Classification and regression output may affect your topology. So there's also another function like softmax that you might want to use for classification. And certainly your typical analog regression output is a consideration here as well. There's a lot of talk about normalization and standardization, and some people talk about this as it's the same thing, but they're really two different things, and there's an important distinction between them. Normalization, and the other thing too is depending on which statistical website or reference you use, you might see them either mixed up or refer to normalization as standardization. Normalization is essentially scaling data between 1 and 0, and I've put the formula here to do this. Normalization can be used for neural networks as well, and depending on, again, the structure of your neural network, it's sometimes more advisable to go -1 to +1. One thing to keep in mind is that 0 is a very important value in a neural network, because remember, what you're doing is you're multiplying that by all the weights. So 0 really means that this has no contribution to the output. So keep that in mind. That's a critical thing to understand in a neural network, is that magical 0. Now, that doesn't mean that if you misuse the 0 that the neural network can't figure it out. What it's going to do is it's going to delay the solution of your neural network, because what the system's likely to do is to adjust the biases to compensate for the fact that 0 represents something other than no contribution. The other problem with normalization is that outliers can impact the range. It'll compress the data. So if you think about this, if you've got a lot of numbers around 0 and you've got one that's close to infinity, what that's going to do is that's going to have that one that's near infinity labeled as 1 and all the others labeled as 0. So normalization can kill your data if you're blindly processing it in that way. The other issue here too is that the mean is likely not equal to 0. So even on the case where you've scaled the data between -1 and +1. So that doesn't necessarily mean that the average of that data set is 0. Again, we'll talk a little bit more about this 0, but if you think about it, what you'd really like to do is you'd like to split the data in half. So you'd like to have everything that is, supporting of your class to be above 0 and not supporting below 0, for example. So that way the system can easily converge and solve your problem. Standardization, on the other hand, is a bit different. It has a similar purpose. It's sometimes called a z-score as well. So in this case, you generate the standardization by setting the mean equal to 0 and the standard deviation equal to 1. And the formula for that I've put here. So essentially you take your data, you subtract the mean from it, and then you divide it by the standard deviation of that data. So just from my experience, this is generally better for pre-processing data. Again, you've got this 50-50 above and below 0. You know, some people might be afraid that it goes above above 1 and below -1, but this is generally okay. You know, because what you're trying to do is you're trying to train a neural network, and that's based upon statistics. So, you know, ultimately 3 will appear as a, you know, the third sigma, you know, for your data set. So it'll only show up, you know, 99% of the time, you know, 1% of the time ultimately. So, you know, that's why standardization tends to be a lot better. Don't be too concerned about the fact that it moves up from -1 to +1. Again, that's generally okay. You just don't want all the data to be there, is outside of that range. The other, you know, portion, you know, to consider again here is the you're multiplying x by w. So if x is 0, then the average has a contribution of 0 to your output. Again, this means that your neural network doesn't really need to modify the bias values to compensate for this, you know, this balance point of your network. And, you know, again, this tends to give better distributions overall. Feature selection. Feature selection, what your goal when you're selecting features is to give information to your neural network. So what is information? Information tends to be variation. So variance or standard deviation would essentially indicate that there's information there. So also the data shouldn't be correlated with other features. So if it's correlated with other features, you're not necessarily giving it additional data. We'll go through an example of that shortly. So an example of non-information would be a 0, just a simple constant value of 0 or any other number. As you can tell that if you just have one particular feature on your chart, which is just a constant, it's adding nothing to the overall information of the system. Ultimately, it will be pushed out of your neural network because there's no information in it. So now if you have two different values like a 0 and a 1, and you know, for half the network it's 0 and half the network it's 1, that doesn't qualify as a constant because it varies over the data set. And in that case it might be important. So let's just run through a quick walkthrough of you know, some data. So here's a chart. This is actually the same chart I used in the last presentation as well. So you know, it just happens to be the CL, and it's a 1-minute chart. So you can see that there's a lot of bars on here. It goes up, it goes down. So one thing you might be able to do is to add an SMA to it. Okay, so you add the SMA that helps point out the you know, the trends in the chart. Now I've put on here that the human eye is going to pick up about 2 million pixels of data out of this particular chart. So as a human, you look at this and you say, wow, there's a lot of data there. So, but now this is generally not what you feed to your neural network. So you might start out with, you know, essentially 1 bar, which is 5 points. So this is what you're feeding your system. Then you might say, well, that may not be enough because I can't even tell what's going on. So you add 10 bars. So you add a little bit more data. You get 50 points that you're feeding the system. But again, what's the output of your network, and what are you trying to do? Do you think that it's fair to feed this input into your system and have it generate whatever output you were expecting? So, you know, for another, you know, like is this a a pivot in the data? Who knows? So you could go through and you could say, all right, well, I'm going to give it every single data point that I have, on the chart and see how it does. Well, now you've got 1,000 data points for 200 bars that appear on this chart. Now, 1,000 data points, the newer systems can handle that, but the problem that you're likely to run into here is you could start to overfit. So you could end up training a system that is very good at memorizing this particular sequence of data. So, as we talk about feature selection, we also need to talk a little bit about stationarity. So, as you can see, from this chart here, the SMA is not stationary. Stationary ultimately means that it has a zero mean, over its time period. And the moving averages tend to not do this. There's a couple of ways you can convert it, and I'd love to say that there's a perfect way to do this, but you just need to experiment with it and see if it gives your system the data that it needs. You can take the first difference, or essentially the derivative of your waveform, and over large periods of time, this is considered stationary. And again, I'm going to repeat that, over large periods of time, it's stationary. So again, if you're in a downtrend, the difference is always going to be on one side of zero or the other. So, and that's technically not stationary. So over a short period of time, your data is not going to be stationary. You can also convert it to a percent change, and ultimately that's just a different version of the first difference. So you could even try acceleration, the second difference as well, the second derivative. So there's a lot of different things you can try, but one thing's for certain is you can't feed it the SMA unprocessed. So the same goes for the other waveforms that exist here too, which is the open, close, high, and low. Feeding those directly into a neural network is not likely to give you good results. It will likely train with that data, but it will almost definitely not generalize. So let's also talk about feature selection in the terms of sensitivity to change. The particular example that I have here is an SMA, and it's actually, believe it or not, a bad example to give to a neural network. So it's essentially the linear addition and subtraction of time data. And you can see if you take the series of 20 with 8 zeros and minus 21, and minus 20 on here, the SMA would be calculated as 0 because the sum is 0, and then you divide that by 10, so the result is 0. Now, as you add one more data point on, so essentially you're going to drop the first 20 that existed in the data set, and you're going to add a leading 0 because that happens to be the next data set. What you're actually going to see is you have 9 zeros and a value of minus 20. So, whoops, and it looks like I did the math wrong, but what you're actually going to get is minus 2 in this case. And that's kind of strange because what just happened is you went from minus 20 to 0. That's kind of an up direction. I would have expected this value to be positive, not negative. So what you're actually doing is you're introducing noise into your system because of the fact that it's subtracting off the older data. This happens to be 10 points old, and the question here is whether or not that's really interesting to your neural network. So be careful of what you're including. Understand what features you're extracting and what noise they might actually develop into your deep learning system. So the answer here is ultimately to use more of an EMA type of thing. What this does is it weights newer data higher than that of older data. The old data tends to just die away with time, whereas new data, I think for a 10-point EMA, is around 18%, as opposed to, in the case of the SMA, where it's a 10% addition. So this is probably less confusing to a deep learning system. Again, depending on what problem you're trying to solve, this is assuming that you're looking at a trend or something like that. then you probably want to weight the newer data more than the older data in that data set. The other consideration that you need to have with feature selection is, do you have too much? So if you have too much, you're likely to overfit. So you need to do what's called feature reduction. So you want to reduce the overfitting. You can do this manually, or you can use tools like the PCA, Principal Component Analysis, which essentially uses the covariance matrix and figures out where the data, what your input data has in the form of information. That's how I look at it. So it finds out where things are varying the most, and it makes that its own feature. And we'll go through a little example here in the following slides. So let's say that we've chosen two features. We have feature in 1 and in 0 as shown here. I've only separated the data. These are identical waveforms. I've just thrown them on two different axes, the secondary axis as well. So I can just separate them so you can see that they both go from 1 to -1. And if you plot each one of these against one another, so you're plotting in 0 against in 1, you'll see that at -1 for in 1 and in 0, you've got the same point. So what you end up with is the data is very well correlated to one another. You end up with a line on this chart showing that for any value of in 0, you've got the same value of in 1. So that's what this line is representing. So essentially with this, I'm going to call it a 0-degree shift. This is the principal component analysis out of that. And you can see there's something that's very interesting that happened. So what the principal component analysis will do is it will return two features to you, but based upon what it considers are more important. So it looks at the data that you gave it, mixes it up, and returns back to you the features with the most information in it, and then it takes the residual of that and gives it to you as the second feature. And you can see here the two features were identical. So what it did is the primary feature actually grew in size. It actually is up here at 1.414, and you can see that the second feature is 0. So what has happened here is, that's the wrong slide. Interesting. So this should be 0 degrees, and what you've got is the PCA 0 is now making up 100% of the information that is being fed into the system. So, and the second feature is 0. So the best thing to do here is to delete this second feature, because it's adding nothing. And that's intuitively obvious. You didn't need to go through that process to understand that. So if both of them are identical, the second one is just going to cause you trouble. And more importantly, the second one is likely to have a little bit of noise associated to it. So you're likely to overfit with that second feature because of the strong correlation between the two. It's going to use that second feature to try to get fine differences in your data. So it's going to use that noise to try to fit better your training set. So as we move on here, here I've shifted the data by about 45 degrees. So you can see they just offset a little bit here. And we're going to do the same thing here. Here is the plotting of in 0 versus in 1. You can see it forms this kind of rectangular box here, which shows that the data is not completely correlated. You can see there's some forms of correlation here, but there's at least two different dimensions to this box. You can also see this is what the PCA returns. So what it says is that it sees two features. It sees a strong feature, which it has here at the PCA 0, and then it sees a weaker feature, which is the PCA 1. So, and you can see that the second feature is much weaker than the first feature. So what it's actually done is it's gone through here and found out where the most, it's created its own feature. So you can see that we have X and Y here. It actually creates its own feature. It'll actually cut a line through the middle of this box and maximize the amount of variance to generate the first feature. And then what it takes is the residual, which is the second feature, which is at 90 degrees to the first feature vector that it had created. And what you end up with here is you end up with 84% of the information in the first feature and 16% in the remaining feature. So what is happening here is about 30% correlation between the two waveforms with the 45-degree shift. So we've ended up with some contribution from the second feature. So this still might be interesting to your neural network. So at this point it doesn't make sense to delete the feature, but understand that the second feature is potentially not giving you as much of a bang as you want. So in other words, you're not giving this 2 features. You're giving it like a feature and a half with the input data. Now let's shift it 90 degrees. So you can see I've just moved this over a little bit more, and now when it crosses through 0 here, it's the peak here, so it's shifted by 90 degrees. So this actually forms a nice square on the X and Y coordinates here of in 0 and in 1. So, and as you can imagine, the essentially the PCA output is if I had a smaller sampling size, these would be almost identical, shifted by about 90 degrees as well. So you think of these two as riding at the same value, you know, through here. So what I've got is what you're seeing here is digital noise, and that's the reason why they don't overlap one another. You can also see here on the chart that the PCA 0 came out at 48% and the PCA1 came as 51%. The noise is causing the fact that you normally would expect the PCA0 to be higher than the PCA1, but this digital sampling, I had a very coarse data set that I fed this thing, and you can see it right here. So there's very few samples that make up this data set, and that's what's causing this kind of this difference here. This would actually be 50-50 if you had enough samples. So now let's talk about shifting the waveform 180 degrees. So just think about this for a second. What do you think the results are going to be when we do this? So we're going to shift the data 180 degrees so they're completely out of phase with one another. So have we maximized the amount of information that we're giving this system? Well, if you plot the two pieces of data against one another, what you end up with a line with a reverse correlation. So essentially the slope of the line is negative, so the correlation is now minus 100%. So, and much like the first example where we were 0 degrees shifted, you end up with the same exact situation. You end up with you know, a primary PCA 0, which is very, very large, and PCA 1, which is 0. So essentially what it's saying is that you've added no additional data by having the second waveform that's 180 degrees out. So here's a case where you can throw out one or the other, and it wouldn't make a difference to your neural network. And it really doesn't matter if you throw out the first or the second waveform, because the neural network is still going to figure out the relationship. It just means that it's going to change the weight on one of them to -1 or minus something. So here's the overall chart of what we just talked about. So you can see again here for the 180 degrees, delete the second feature. All it did was adjust the magnitude of the output waveform. This is identical to the results we got on the 0 degree shift. So just because data doesn't overlap with one another could indicate that it's not being used for your neural network. And in this case, including these two waveforms 180 degrees out of phase, as well as the 0-degree one that we had where they simply overlap, neither of those are adding additional information with the second feature. So it's a waste of computing resources and time. So that's a little bit about PCA. PCA is a principal component analysis, which is going to help you reduce the amount of duplicate information that you have in your network. So I'll just give you an aside. I had a random data set that I had created which had 189 features to it. Well, I ran it through the PCA, and what I did is I set a threshold of about 1%. There had to be at least 1% contribution to the end result with the PCA features. And what that left me with is only 18 features. So the 18 features made up all of the 189 data points that were being fed. So that was a little bit of an eye-opener to me as well. So, and you can imagine that that data set included a lot of SMAs, EMAs, a lot of similar things like Bollinger Bands and stuff like that. So in other words, what it found is correlations even between feature types. So, and it reduced it down to about 18 features. And if you wanted to go to something like 5%, I believe that number dropped to somewhere around 6. So, you know, there wasn't a whole lot of information in the 189 features that I was feeding it, but there was a lot of data. So, and from a computational standpoint, it makes a huge difference when trying to train a neural network. So I guess the moral of this story is to understand your data, and the best way to do that is to actually visualize it. So go through each and every feature that you're feeding the system. So I like a tool called Weka. The URL is down the bottom here. This is essentially an open source Java application where you can import like a comma delimited data set. They have a couple other data sets as well that you can import. And then you can rapidly visualize it. You can see on the left here, you can check the distributions of the different features that you're feeding it. And on the right, you can actually see it actually draws that X versus Y for each of the different feature sets. Because as you add additional data sets, features to your data set, all you're doing is the same problem that we had here, only with additional dimensions. So it starts to get more and more complicated, but you can even see here in this small little image that we have a lot that are correlated with one another. I believe that this is actually the 189 features that I imported here as well. So now let's talk a little bit about the results of your network and what to do about them. So this is probably more important than some of the other things that we've talked about. Although feature selection will directly impact this section, this is the same curve that I've used in the past, is that ultimately I have a function which is y equals x minus 50 squared. So that's the function that I'm trying to approximate. So this isn't curve fitting. This is actually has approximated this function, and it's done very well at it. So this is almost a perfect fit. This is what you're looking for. So this would be called convergence in your neural network. So it has converged to an answer. So the one thing to realize here is there's no test data, so we can't tell if it's generalized, but presumably we've left a few data points off at the end here, and this data has also generalized. Here's an example of what convergence might look like between testing and training data. So the training data you can see is ultimately epochs is the x-axis, and essentially profitability is the y-axis here. So you can see that in the training situation here, you can see that training goes up and it becomes more and more profitable. And more importantly, what you can also see is that the test data set is doing almost the same exact thing. So this is convergence with generalization. So the generalization is what you're looking for. You can converge all day with your neural network, and it buys you absolutely nothing unless you want to repeat it with the exact same data that you trained it with, which is generally not what we want to do in the stock market data. It usually doesn't bring a lot of value. Overfitting. Overfitting is very, very common these days and tends to be the biggest reason why people don't get good generalization of their data. And that's because computers are allowing us to create very large networks, so we don't really pay attention to all the data that we put in, and we end up with what's called a high variance fit. So in this case, what you're going to get is a very low training error, and you're going to get a very high validation error, or test error. So what we've done is we've overfitted this data. So you can see that this red line has these weird, oscillations in it, because it absolutely matches the diamonds, which is the samples that we fed it for training. So, and you can see this error, this precise black squiggle that I've put in between each one of these teeth, so is part of the error, but it doesn't show up in our training because it's done such a nice job creating this very complicated red line to match all of our training data. So that's essentially what's happening when you're overfitting. So you're creating such a complicated curve that it absolutely matches your training data set. But if you try to add a point anywhere in between, you're going to get a very large error because the curve has just so many dimensions of freedom that it has done something completely different than what you would expect. So it will not generalize between those data points. The frustrating part you can actually see down at the bottom here is if you train a network, you might actually get pretty good validation data between, say, 40 and 60 on this chart, because you can see that that function isn't as strong in that area, and it looks like it generalizes well. But if you try to new data out at 120 to, say, 160, what you're going to find is that the data falls apart, and this is usually what happens over over time, is that you've trained your data between 40 and 60. You think you've got pretty good validation results in that area. Even a walk forward has done pretty well between 60 and maybe 80. It's starting to not look so good. But then you let it go live, and you find out that the curve that you've generated here is it just starts to fall apart rapidly, and you no longer get the desired output. So overfitting. Here's an example of what an overfit might look like coming out of a neural network. So essentially you've got your training profit and your test profit. So what you've got is your training profit starts to take off and you're all excited, but your test profit is diving and getting worse and worse over time. So that's a strong indication that you have an overfit of your data set. So there's a couple of things you can do about this. Here's another example of an overfit data. You can see that the training data starts to take off again, and it goes up, and at that time it also has the testing profit decreasing. So this is what's called an early stop. How you'd fix this, you would simply just truncate your network back to the point in time before the testing profit started diverging. So this would have to be done manually or visually, and generally requires that you store data at a certain epoch rate so that you can revert your network back to that point in time. So with this red line, it is probably a pretty good point to revert this network back to get a half-decent convergence and generalization of the test data. Certainly if you just run this longer and longer, the neural network is designed to try to get a better fit on its training data. So what it starts to find is little tiny pieces of noise that it can piece together that we talked about earlier, and it starts to increase its output. but at the same time what it's doing is no longer generalizing because that same noise doesn't exist in your test data. So the test data starts to decrease, whereas your training data starts to increase because of that matching of noise. Underfit. This is less likely the problem with most neural networks, but it can still happen. So what happens here is that your network isn't big enough. Oh, wait a minute. Before I go on here, I don't think I talked about ways to fix the high variance or overfit. There's a couple of different ways you can increase your likelihood of avoiding this situation. So some of the easiest ways to do it is increase the number of samples. So if you had more samples that would be like in between these points, it's clear that this curve would not look the way it does today if there were additional training data points. You could reduce the number of parameters. So what you might actually have is way too many features as your input. So much like the 189 features that I had that reduced to only 18, that could be the problem here too. So you're just simply feeding it way too complex a vector, and it can match that until the cows come home to any number of random data points. Regularization is another opportunity. This is where you're adding a penalty on weights. So there's some of the newer tools have this built in, and you can enable it or set the level at which you want. But ultimately what you're doing is you're multiplying your input times some weight matrix, and generally how you get some of these weird functions is some of the weights start to move up in value, so they start to explode. And regularization helps to reduce that by penalizing your network. It essentially increases the cost of your network by the actual value of the weights in your network. So what it's encouraging is lower weights. Early stop, we talked about that already. Dropout is another one. I haven't seen it successfully done in anything other than a convolutional neural network because of the amount of redundancy in data in a convolutional neural network. But there's no reason why dropout may not work in a regular deep neural network or potentially even a recurrent neural network. Dropout ultimately is where during the training phase only, you're randomly dropping samples. And what this is doing is this is forcing the neural network to learn additional ways to generalize to the same data. So if you think about it, if you had one feature that the system always grabbed hold of in a dropout situation as you're training, that feature would be randomly dropped at some percentage. Normally people use about 50% dropout rate. My experience so far has been that by using a high dropout rate, what you likely will get is an underfit. So this is another way to simulate an underfit, is by dropping out too much data, it can't get enough information to build its neural network. So the other way you can deal with this this level of high degree of variance is by reducing the network complexity. So what most people do is they build a very large network to make sure that they converge, but the problem is that will end up biting you if you don't have enough samples. So you either really need to increase the amount of samples that you're going to feed this thing, or you need to reduce the network complexity. And some of the learnings that I've read online is that you're usually, in the case of deep neural networks, better off increasing the depth than the width. So if you want to experiment with a more complicated network, try depth over width. So that's probably one of the best learnings, because by adding essentially depth, you're adding a major factor in the amount of generalization that can occur, and it actually will create a higher abstraction to that of the previous layer. Whereas if you're just adding additional nodes on the same layer, all you're doing is getting additional features at the same abstraction level. Whereas what you'd really like to do is to bring this closer and closer to a final abstraction that you're heading for as your goal. So we talked about those two, and again, here's the underfit. You can end up with an underfit if you delete too much data, and that's where the dropout ultimately left me with some of my experiments. I ended up with an underfit because it couldn't converge. The network just couldn't converge. So what you're likely to do with an underfit, or the indications are, you're going to end up with a high training error and a high validation error. So that's what you're seeing here, is essentially the data that, or the fit that it comes up with, is a straight line. So in other words, you didn't have enough dimensions in your potential solution. So it couldn't actually meet this curve. All it can do is try to balance this curve so the area above and the area below are equal. And that's what it would end up doing, is it would give you this one line as your solution. And you can see there's only one point right around here where you would end up with good data. So everywhere else there's a significant error from the actual data point. So here's kind of an example of what an underfit might be. So underfit is better done with cost data. I didn't have the cost data to throw up here, but ultimately underfit, if things just simply aren't moving, if there's a small variation at the start of training, whereas ultimately what it's doing is it's trying to figure out where to position this line. You'll see some improvement early on in the training cycle, but then the system will just flatten right out, because there's absolutely nothing more it can do, to improve the situation. So essentially, if you're ending up with a flat, neural network with very little activity that went on, and also if your cost is not decreasing, then what you've most likely got is an underfit situation. So again, in that case, what you need to do is you need to add more parameters and increase the network complexity so that it has more data to be able to match this curve. So that's all I have. So if Terry, if you're still awake, and anyone else still on the webinar, if you have any questions, I'll try my best to answer them.
Okay, there are a couple. Just give me 1 second to get situated. You caught me with a mouthful of cashews. So.
Actually, I have a box of them here as well, so sounds like a good idea. I
keep them in the bottom drawer of my file cabinet, so I ever need a little salty snack. All right, let's see. What programming languages and tools are you using?
Okay, I'm using TensorFlow is the main deep learning network that or system that I'm using. TensorFlow is based around C++, which is not as much of that as there is Python. So Python is the core language. C++ is mainly used for what's called the inference. So the inference is where you've got your model, it's built, now you want to run it real time. So what you need to do is you need to have a very high efficient C++ code, which simply just takes the input and replies with the output. So and then certainly I have C# code back on the NinjaTrader platform as well, because I have got NinjaTrader connected to a Linux box through a TCP/IP stack into TensorFlow to process the data and return a result back to NinjaTrader. Wow, it put you to sleep, huh?
Let's see. Is there any way to deploy these neural network building blocks within the context of any backtesting or trading platform? Are you aware of any platforms that support these?
Yeah, TensorFlow does. The Microsoft product, I believe, does. I don't know a whole lot about them, you know, the additional products, but I'd say that the basic building blocks that I talked about should exist in anything that calls itself a deep learning, you know, tool. So they're just they're basic functions. What you might not find is some of the hybrids of some of those features or some of those building blocks, because again, those are the base versions of those building blocks. So there's an enormous amount of variation from there, and there's tons of research papers that talk about, you know, how to gently modify some of these to get different results.
Okay. Should outliers be capped to some rule of thumb like 6 Sigma?
I don't have a good answer for that. I would say that this is again where you're going to need to put your detective hat on, and you're going to need to try it and see if you get a better result. I guess I'd first question why you end up with an outlier, and maybe that whole data sample is just invalid. So, you know, for example, if it's a division by 0 for some reason, then it's unlikely that you know, what's called the gradient is valid at that point with a division by 0. So that's likely to throw off your neural network to begin with. So because neural networks are trained based upon essentially the gradient of the output back to the input. So, and if you end up with outliers, it's possible that you could have ended up with some kind of corrupt data. And this is where you need to look at your inputs, and you might want to discard that data sample. So I'd say there's 3 different things to try. Discard the data, clip the data, and then certainly try it the way that you've passed it to see if you get different results during the training phase.
Okay.
Your generalization will certainly tell you, as well as your error, you know, your cost for the training system.
Okay. When computing z-score for standardization, do you sample mean and standard deviation separately for training, testing, and real-time observations?
Let me think about that. Let me look back at that. So I think the answer is that however I train the system, I use as the fixed data. But I just want to run back. So when I standardize, yeah, because what you want to do is you want to assume that it's the same distribution. So X makes up some distribution of your training data and any future data that is going to be X. So X has to represent your distribution. So that means that you would use the same mean and standard deviation that you had from your original training set. So those would be constants through this whole thing.
Let's see. I'm trying to... Do you have any experience with using genetic algorithms to find robust patterns or profitable strategies on market data and a predictor, indicators, for example? And what are your thoughts on that?
Genetic algorithms, I played with those years and years ago. I did not find a great means to utilize those, and I think the issue is because of its ability to generate layers of features. Because if you think about a genetic algorithm, it might be a very shallow network, and that means that your abstraction of features that it's looking for might not be able to go deep enough. So I would say it completely depends upon what you're trying to do with genetic algorithms. You know, I did generate one that had a pretty good idea of whether or not there was a trend up or down based upon tick data, but I can't say that it was very useful over the long run because to me that's the kind of the issue is the horizon for some of those tools, because you're processing data here and now and you're processing data that is very noisy. So you're likely to get results as of now and not where it's headed in the future. Not to say that you can't restructure your input and be able to do that, but it might be easier to use a deep learning system as maybe a front end. There's no reason why you can't use a genetic algorithm in parallel with a neural network as well. You know, we've seen a few of those. I don't know who's seen the news, but when the I think it was DeepMinds that came out with the neural network that solved the Go problem. So ultimately it played Go, which is a very complicated board game with a very high level degree of complexity. In that particular case, they actually used two networks. So they used one for pattern recognition and another one to determine whether or not what it should do in response to that. So they actually had two neural networks that they had traced to solve the problem, and there's no reason why you can't do that in any solution.
What do you use for a threshold cutoff when evaluating the PCA features?
Again, this is one you need to play with. I generally use 1%, but I've almost seen that there's still very little value to some of those features that you might even want to go with like 5% or even higher. Again, this is one of the what I'll call meta parameter of your network that you need to adjust. It probably also depends on how many features you have coming in as well and where the answer to your problem might live. You do run a small risk that you lose the information if it's a very subtle feature that you're trying to find. So there's a possibility you lose it, but you know, if you're down at 1% or less, it's likely to be very, very, very long time before your neural network detects that feature, and you manage to get a system that converges and generalizes. So you're almost better off finding a better feature input than trying to use some lower level features.
Have you looked at stacked autoencoders to initialize neural networks?
Not to initialize. So there's some quite a bit of papers out there, and you know, some people have integrated autoencoders as a means to reduce noise on the input data set. So you know, that would certainly be a valid approach. I haven't had any time to really play with that, but you know, ultimately from what I've read is you'd use the autoencoder, you would teach the autoencoder, and then you'd cut it in half, and you take the output of that pinched section as now your input to the neural network. I would say that that's fairly close to what a PCA does, only it would be a non-linear type of PCA, which might actually work better in some cases. I'd say try that. That's something that's on my list of things to look at, but that's out a little bit.
By their nature, oscillators can be easily normalized, standardized, but what are best practices for normalizing and standardizing price action data like moving averages, swing, and zigzag indicators?
Yeah, again, it depends on what you're trying to get as an output, but what's important to think about here as you're designing your features is whether or not data is independent from one another. So in the case of the zigzag, the length of, you know, each leg might actually be important to the overall feature detection and what happens next. So I'd be careful normalizing to or standardizing against one particular leg, and what you may want to consider is actually taking the total length of all legs. So that's another way to normalize that data set, and that's how I've done it in the past, is to normalize against the total distance that it's traveled, because now each leg is going to give you a ratio of the overall portion. So now, you know, I've seen this question in my past too. The question is how do you get magnitude in if you're normalizing like that? Well, sometimes you have to give up on one thing or another, but another way to handle magnitude is to potentially give a binary input, which gives a degree of scale. So let's say you have, like a very small, medium, large, and huge type of signal. So what you might want is a binary classifier for each one of those. So you'd put an additional 4 features into your network, and you would set the first one to 1 if it was tiny or small, and then if it's medium, you'd set the second one to 1 and the first one to 0, etc., all the way through. So you'd end up with 4 features that are either 1 or 0, and only one of them would be a 1, based upon the intensity of the data. Now this also depends on how you're training it as well, but that's generally how I would probably approach the magnitude concept in case you're having generalization problems to like the unseen leg, which I believe is probably the task at hand here.
Do you think DNN works better with futures, equities, or Forex?
I'm sorry, DNN? Was that the question?
Do you think DNN works better with futures, equities, or Forex?
Okay, that's again going to depend upon what your problem is. So here you're looking at a particular building block without a problem. So without knowing the problem, it's difficult to answer that question. So, but I'd say it's a general purpose. It's a DNN structure might be the easiest to get started. What you might find is that you can't quite get as good an output as you're hoping for, and then you're going to need to move to CNN or an RNN or some other complicated, DNN type structure. So I guess to answer that question, I would say that it really doesn't matter what the equity is, because from a pure statistical purpose, they're all going to be handled the same way within the network. It's how you're going to pre-process the data that might change.
Convolutional neural networks have a novel way to look at groups of pixels to form higher levels of extraction. How can this approach be used for training applications to get higher levels of abstractions?
I'm going to leave the solution up to the student on that one. So, but think about that. What can you make a 2D image out of and feed into an input? Unfortunately, that's one of my areas of research at the present time, so I'd rather not give any more detail other than that.
Can you point us to a case study, blog post, article, etc., that takes us through a sample analysis start to finish?
A sample analysis. I certainly wouldn't know it offhand. I'd have to go find one. But what would probably be best is to take that question and have that person post it on the webinar thread so that I can follow up to see if I can get more information. And I'll see what I can find. There are tons of papers out there on just about every topic.
Okay.
So I'm sure we can find something that might help.
Okay. In line with that, there's also a couple questions. I'm going to try to combine them to one, asking if there are any groups or forums sharing and discussion of this information. And one says, when you said a lot of what you're seeing people do, are you talking about other groups or communities that you're seeing online that are that we can use to start building relationships?
Yeah, I see. I read a lot of research papers, so I'm saying that probably some of the research is what I'm referencing there.
Okay.
I really don't see a lot of people open and sharing about stock trading and such. There's a lot of people out there. There's a Google's I think TensorFlow group. Stack Overflow is another great place to get information on just about anything in this area. And if I think about it, I'll post a few of those and any others I can think of on the site, on the webinar thread.
Okay. Okay, I'm about to probably gonna botch this word, but I'll do my best. Have you tried the Boruta library to find features that are most important?
Yeah, I haven't done any of that yet. What I'm hoping is that's one feature that is going to come to TensorFlow in the future. I started trying to research that myself to see if I could do it. It's not an easy calculation, as what you're trying to do is you're trying to follow. It's a sensitivity analysis based upon your output, and unfortunately, it's also based upon how close you are to having a good solution for your output. So, trying to find the most important input features based upon your output is only valid if the weights in your network are valid. So you would have to go through some training mechanism. You might not have to go 100% of the way through, but you would have to probably train your network for some period of time to get a half-decent answer, and then perform one of these sensitivity analyses upon the output and drive the answer back through to the input. Ultimately, what you're using is the gradient descent, or the gradients backwards, based upon a couple of different inputs to see what the sensitivity of the input is to that particular output. So the answer, I guess, is no.
Let's see. Are you retraining your network with real-time data?
If the question is around whether or not it's an online learning, right now the answer is no. That's a little more complicated to do, but it's something I intend to do in the future. So if that's not exactly what the core of that question was, then if they could either re-ask it or post it to the website, that would be good.
Okay. And let's see. You mentioned that I should add a layer to a BPNN versus adding nodes to a layer. That normally makes the network geometrically larger and cause the training to take days versus hours to finish. What is the advantage of increasing the complexity in this way?
Yeah, adding additional layers adds layers of abstraction, whereas if you're adding width to a layer, all you're doing is gaining the possibility of overfitting. So you really aren't gaining any additional knowledge about your data. All it's doing is saying, hey, I see a different feature here, but it's at the same abstraction level. So in other words, if you were looking at visual items in the case of an image processing system, then by adding width, all you're doing is you're saying, all right, I detected an eye, but now I'm adding a little bit of more width rather than depth. So now I got an eye that's open and an eye that's closed. So in actuality, what you really want to know is that eye part of a face? And to do that, you need to abstract to the next level to be able to have the neural network learn that an eye with another eye and a nose and a mouth forms a face. So that's what I mean by one more layer of abstraction through a neural network. And whoever asked that question, maybe post on the web or PM me to tell me what tools they're using, because my experience is that adding another layer of abstraction is generally, certainly it's a little more computation, but it shouldn't be all that bad. So because it should be linear being added on.
Were you able to make a profitable system with DNN, and is this kind of rare?
I have made a profitable system with DNN. I still don't like the overall solution because it's not as consistent as I would hope it to be. So essentially the drawdown isn't what I'm hoping for. That doesn't mean that I can't get a DNN to work better, but I've moved on to other approaches and left that behind. So to answer your question, I would say a DNN can solve this problem. You might need to do a little more work on your input to get it to work, whereas like an RNN type of system might help simplify that process. But by going to an RNN cell, you end up with complexities in training and a couple other things because there's some hidden data within it, and depending on how your training network is set up, it can be sometimes difficult to make sure that the proper next state is available for the RNN cell. So, so again, that was the long answer of yes, I believe that a DNN can work, but you need enough sufficient layers for abstraction, and you need to make sure that your input data is very clean and very clear in the way of what features it's trying to generate.
Have you done any work using polynomial regression? If so, can you comment on the efficiency?
I can't say I'm that familiar with the concept, so I'm going to say no.
Do you find it easier to build classification or regression-based neural networks to drive down error and improve accuracy?
Yeah, that's an interesting question. I've been, for most of the time I've been using classification, but I've, given the fact that deep neural networks seem to perform much better and they're likely to generalize better, I think I'm going to go and try some regression as well. So because I can't see why it, again, if you have the right input data, why it might not be acceptable as well. The question is how much noise do you get on the output, and that would be a process of validating that your model works. So, but I would say that right now I use a lot of softmax type of outputs on my back end. So my output tends to be a softmax, as opposed to a regression. But believe it or not, I train kind of more of a analog system, which generates that softmax. It's just my output tends to be more classification than regressive output.
This is going to be the last question because we're butting up against 6 p.m.
Okay.
If we did not get your question, please go to the thread on FIO and ask the question there, and because I'm sure Greg will answer it when he has time. This question is, could you elaborate on the results so far? In other words, does machine learning add something to the table with regard to trading?
I would say that I've traded for a little while, and I'm unfortunately an engineer and I get very distracted. It's difficult for me to focus on a screen for any length of time without thinking of something cool that I'd really like to do. So from that standpoint, I'd say that the neural networks that I've generated trade much better than myself. So hopefully that answers the question that, yes, deep learning I've been much more successful with than any of my other approaches, like the genetic algorithm and some of those that I've posted on Futures.io in the past.
Okay, perfect. Well, thank you for your time and for this great wealth of information for today's webinar. We really appreciate it.
Well, and I appreciate the invite back, and maybe we can do another one in the future with something a little closer to application.
Well, I know early next year, maybe when TensorFlow is more stable, I would definitely love to do a webinar on that.
Yeah, with the Windows version of that, I think might work out well. So, all right. Well, thank you very much.
You too. Thank you.
Okay. Bye-bye.